Welcome, welcome. It's so good to have you here tonight. There is a fire that has been burning for 4.5 billion years. It has never gone out. It has never needed fuel delivered. It has never once flickered in the dark. And yet, not a single human being, not one knew what was actually feeding it until fewer than 100 years ago. Tonight, we are going to find out. Before we drift any further, if these quiet nights of wondering feel like home to you, if science told softly is the kind of thing that helps your mind settle and slow, you might like to stay a while. A gentle tap on the like button helps more people find this place. And if you subscribe, the next quiet night will know how to find you. The little bell ring, it not for noise, but for the next story, waiting in the dark. Now, let's begin. Go outside tonight if you can, or just close your eyes and imagine it. The sky is clear, the stars are sharp and cold, and somewhere above you, invisible for now, because the earth has simply turned away, the sun is still there, burning, impossibly patient, impossibly steady. Most of us never stop to wonder about it. The sun rises, the sun sets. It warms the grass and the back of your neck on a summer afternoon. It makes the tomatoes grow and the rivers run. We take it in the way we take in breathing, without asking why. But here is a question worth sitting with tonight. How does something burn for 4.5 billion years? Not 4 million, not 400 million. 4.5 billion years, a number so large that the human brain genuinely cannot feel it. If you counted to 1 billion at one number per second, it would take you over 31 years. To reach 4.5 billion, you would need to start counting before the first modern human ever walked the earth, before Homo sapiens, before most dinosaurs, before even the earliest fish pulled itself through ancient water. And during every single one of those seconds, the sun was already shining. Here is what makes this so remarkable. Everything we know about fire, everything tells us this should be impossible. When something burns, it consumes itself. A candle burns down. A log chars and crumbles. A forest fire leaves ash where trees once stood. Even the largest fire we can imagine follows. This rule: fuel goes and heat and light come out, and eventually the fuel runs out. So, what is the sun's fuel, and why hasn't it run out? For most of human history, we didn't even think to ask. The sun was simply given. A divine gift. A god in many traditions. Something that preceded questions or made questions seem unnecessary. The ancient Egyptians called him Ra and built their entire civilization oriented toward his movement across the sky. The Greeks gave him a name, Helios, and imagined him driving a golden chariot pulled by fire-breathing horses across the vault of heaven each morning. The Aztecs believed the sun required nourishment, and that without sacrifice it would stop moving, and the world would end in frozen darkness. These are not stories of ignorance. They are stories of genuine, careful human observation, wrapped in the only language their cultures had, for things too large and too consistent to explain any other way. When you watch the sun rise and set every single day for your entire life, and every generation before you did the same, and the sun never once fails, you don't reach for chemistry. You reach for something sacred, and for thousands of years, that was not only understandable, it was in a way the most rational answer available. Have you ever noticed how the sun feels different depending on where you are in the world? Standing in the Arizona desert in July versus standing on a winter morning in Maine, same sun, entirely different sensation. That difference is entirely about angle and atmosphere, not about the sun itself changing at all. The sun is in fact almost perfectly constant. Scientists call this the solar constant, approximately 1,361 watts of energy falling on every square meter of Earth's surface at the edge of the atmosphere every second with almost no variation. Almost no variation. For 4.5 billion years. That kind of consistency is not something a burning log can offer. It is not something any fuel we can hold in our hands could produce. And that quiet, relentless steadiness is precisely what eventually drove scientists to the edge of what they thought they knew, and then finally passed it. But let's not rush, because part of what makes the real answer so extraordinary is understanding just how long and how hard some of the greatest scientific minds in history struggled to figure it out, and how confidently, how completely they were wrong. The story of the sun is not just a story about nuclear physics. It is a story about the limits of human imagination and the slow, sometimes humbling process of expanding those limits. In the 1800s, a period when science was transforming the world with astonishing speed, when steam engines were revolutionizing industry, when Darwin was writing about evolution, when geologists were beginning to read the deep history written in stone, the question of the sun's energy source finally became a scientific question rather than a religious one, and the answers that emerged were brilliant. They were careful. They were mathematically rigorous. And it would turn out spectacularly incorrect. Think about what scientists in the 19th century actually had to work with. They could observe the sun, measure its size, its distance, its brightness. They could estimate how much energy it was pouring out every second. They could apply the laws of thermodynamics, newly developed and freshly sharp. They could reason about gravity, about heat, about chemistry. And they did all of this with genuine brilliance. The problem was not their intelligence. The problem was that they were reasoning from the edge of a map that was about to be redrawn entirely. The greatest minds of the era, men like Lord Kelvin the physicist, whose name still graces our temperature scale, and Hermann von Helmholtz, one of the most rigorous thinkers of his generation, applied everything they knew to calculate how old the sun could possibly be. They considered the most obvious possibility first chemical combustion. What if the sun were simply burning like a vast ball of coal or some similar fuel? The math came back quickly. A sun made entirely of the best fuel imaginable, burning as efficiently as any fire on Earth, would exhaust itself in roughly 5,000 to 10,000 years. Not 5 billion, 5,000. The sun would have burned out before the pyramids were built, so chemical combustion was immediately ruled out. The sun was plainly far older than that. Helmholtz and Kelvin turned to a different idea, one that was elegant and physically sound: gravity. What if the sun were slowly contracting under its own immense weight? As material falls inward, it converts gravitational potential energy into heat and light. This is called the Kelvin-Helmholtz mechanism, and it is a real process. Stars actually do use it at certain stages of their lives. Kelvin ran the numbers carefully. A sun slowly shrinking, contracting perhaps 40 meters per year, an amount completely undetectable to any instrument, then available, could produce the observed solar luminosity for roughly 20 to 40 million years. 20 to 40 million years. That seemed enormous. That seemed like more than enough. But it wasn't, not even close. Because at almost exactly the same time that Kelvin was doing his calculations, geologists were doing theirs. Charles Darwin, working on the theory of evolution, had estimated that the erosion of certain geological formations in England had taken at least 300 million years. Darwin actually removed this estimate from later editions of On the Origin of Species, partly because of the tension it created with Kelvin's solar calculations. Other geologists were finding similar things: sedimentary layers, salt concentrations in the oceans, the cooling of the Earth's crust. All of them pointed to an Earth far older than 40 million years. Some were suggesting hundreds of millions. A few were already beginning to whisper about billions. There was a direct, uncomfortable conflict. Either the geologists were wrong, and the Earth was only as old as the sun allowed, or Kelvin was wrong, and there was some source of energy in the sun that no one had yet imagined. For a time, Kelvin won the debate. He was the most prominent physicist of his era. He spoke with absolute authority. He believed with the certainty of a man who had done the mathematics that the Earth could not be older than a few tens of millions of years. He said so publicly repeatedly and did not waver, and he was wrong. There is something quietly important in that story, something worth holding for a moment before we move on. Lord Kelvin was not a careless thinker. He was not working with bad data or lazy logic. He applied everything that 19th century physics had to offer, and he applied it brilliantly. The problem was that there was an entire realm of physics, nuclear physics, that did not yet exist. The rules he was using were the right rules for the world he knew. They simply could not account for a world that had not yet been discovered. And this is how science actually moves, not always in clean, triumphant revelations. Sometimes in long stretches of confident wrongness, followed by a discovery that doesn't just correct the old answer, but dissolves the entire framework the old answer was built on. The discovery that would dissolve Kelvin's framework was already beginning to stir in laboratories in Paris and Montreal and Cambridge. A new kind of energy was being found, energy locked inside the atom itself. Energy that dwarfed anything chemistry or gravity could produce energy that would eventually finally explain how the sun had been shining for 4.5 billion years without running out. But before we arrive at that answer, there is one more piece of the old story worth understanding, because the conflict between Kelvin and the geologists was not simply a disagreement between disciplines. It was a window into something deeper, the way our assumptions about the world constrain what we are able to see. Kelvin assumed that the laws of energy he understood were the only laws of energy that existed. That assumption was reasonable. That assumption was also the very thing that kept the real answer invisible. Ask yourself, what assumptions do you carry so quietly that you never think to question them? That is not a rhetorical question. It is the question that drives all of science forward. It is the question that a handful of physicists in the early 20th century were beginning to ask almost by accident in the glow of newly radioactive laboratory materials that seemed to produce energy from nowhere, which is to say from somewhere no one had yet thought to look. The light falling on you right now, the light that passed through your window this morning, that warmed the dust on your windowsill, that caught in your coffee and made it glow amber, that light has been traveling for 8 minutes since it left the sun's surface. But the energy that produced it began its journey far longer ago. In the sun's core, in the unimaginable pressure and heat at the very center of a star. In a process so small, it happens between individual atoms and so vast that it powers everything we have ever known. That process, that quiet, ancient, incomprehensible process, is where we are headed next. Because the mystery of what makes the sun shine is not really a mystery about the sun. It is a mystery about matter itself, about what lives inside the atom, about what the universe chose to do with hydrogen when it had 4.5 billion years and enough gravity to press it into something new. Let's go find out what that something is. And that question, what lives inside the atom, is one that no one in the ancient world could have possibly imagined asking. Because for most of human history, the sun was not a physics problem. It was a presence, a power, something that arrived each morning without explanation and demanded not understanding, but reverence. Tonight we are going to spend some time in that older world, not to dismiss it, but to understand it. Because the stories people built around the sun were not primitive. They were in many ways the most sophisticated responses available to minds that were observing carefully and reasoning honestly. And some of what those ancient watchers understood about the sun still quietly shapes the way we see it today. Let's begin in Egypt. Around 5,000 years ago, along the banks of the Nile, a civilization was constructing something that has never quite been equaled for its integration of architecture, religion, and astronomical observation. The Egyptians did not simply worship the sun as an abstract deity. They watched it with a precision that bordered on scientific. They knew the sun rose in a slightly different position on the horizon each morning. They tracked the yearly cycle, the slow drift northward after the winter solstice, the long, high summer days, the return of darkness. They knew exactly when the annual flooding of the Nile would come, because it coincided reliably with the heliacal rising of a particular star Sirius just before dawn. And they built their temples, their tombs, their entire sacred geography in alignment with these movements. The great temple of Abu Simbel, constructed for Ramesses II, around 1264 BCE, is one of the most precise astronomical instruments ever built in stone. Twice a year, on February 22nd and October 22nd, dates believed to correspond to the pharaoh's birthday and coronation, the rising sun penetrates a corridor 65 meters deep. and illuminates three of the four statues in the innermost sanctuary. The fourth statue, representing the god of the underworld, remains always in shadow. This is not accident. This is observation applied over generations, encoded in sandstone, made permanent. Think about what that required. No telescopes, no calculators, no written astronomical tables. At first, only careful human eyes generation after generation, watching the same horizon, recording the same movements. Learning the sun's patterns the way you might learn the habits of a neighbor you have watched for decades. Rhea, the Egyptian sun. God was not a simple character. He was a layered, complex, evolving figure who merged with other deities over centuries. In his morning form, he was Khepri, the scarab beetle rolling the sun across the sky, the way a beetle rolls a ball of dung, an image that sounds humble but was profound, because the Egyptians had noticed that scarab beetles roll their balls from east to west and lay their eggs inside them, and the young emerge from within. Birth journey, death renewal. The sun's daily arc mapped onto the most common insect in the desert. In his noon form, he was Ra at his most powerful, the blazing life-giving force at the height of the sky. And in his evening form, he was Ra Atum, the setting sun, descending into the Duat, the underworld, where he sailed through 12 hours of darkness on a night bark battling the serpent Apophis chaos disorder, the force that would swallow the light before emerging again at dawn. Every night Ra fought chaos. Every morning, Ra won. And the Egyptians took part in that battle. Their rituals, their prayers, the layout of their sacred sites, all of it was designed to support Ra's journey to lend cosmic weight to his nightly struggle. The sun did not rise automatically. It rose because the right things had been done. This is not irrationality. This is a deeply human response to a genuine observation. The sun is necessary for life. The sun follows a pattern, patterns can be disrupted, and therefore the pattern must be maintained. The logic is sound. Only the mechanism is wrong. And that kind of reasonable wrongness, careful observation, correct conclusion, incorrect mechanism is something we will encounter again and again in the history of science. Now, travel east, across the Mediterranean and into the Greek world, where the sun acquired a different kind of mythology, one less focused on maintenance and more focused on meaning. Helios. The Greek sun god was the driver of the solar chariot. Each morning, he yoked 4 fire-breathing horses to his golden vehicle and drove them across the sky from east to west, then sailed back through the river Oceanus that encircled the world to begin again. He was not the most powerful of gods. Zeus held that position, but he was the one who saw everything. Helios was the witness of the world. When the gods wanted to know what had happened in some distant place, they asked Helios because his chariot passed over all of it. This is an interesting detail that is easy to overlook. The Greeks connected the sun not with creation or battle, but with visibility, with truth, with the impossibility of concealment. To stand in sunlight was to be seen. To commit a deed in daylight was to commit it in front of a divine witness, the sun as the guarantor of transparency, of accountability. That idea persisted. It passed into Roman religion, where Sol Invictus, the unconquered sun, became one of the most important cults of the later empire. It passed into early Christianity, where the imagery of Christ as the light of the world drew heavily on solar symbolism. The winter solstice, the rebirth of the sun's power after the year's longest night, became entangled with the birth of Christ in ways that church historians still debate, and it passes into our language. We say someone is a shining example. We say brilliant people are luminaries. We call wisdom enlightenment. Even now in the 21st century, when we know the sun is a middle-aged G-type star powered by nuclear fusion, we still reach for solar language when we want to describe something true and good and clear. Have you ever noticed how uncomfortable it feels to be somewhere without natural light for too long? Not just inconvenient, but genuinely unsettling in a way that is hard to name precisely. There is science behind that feeling, and it is older than any culture's mythology. Human circadian rhythms, the internal clock that governs sleep wakefulness, hormone production, digestion, mood, are calibrated to the sun. Not to any sun we invented, to the actual sun, its actual spectrum of light, its actual daily arc. When that rhythm is disrupted by shift work, by windowless spaces, by the artificial blue light of screens at midnight, the consequences are measurable. Elevated cortisol, disrupted melatonin, increased risk of depression, metabolic disorder, cardiovascular disease. The ancient Egyptians did not know about melatonin, but they knew in the way all living things eventually know that the sun was not optional. It was not one good thing among many good things. It was the ground everything else stood on. That knowledge felt in the body before it was ever written down is part of why sun worship arose independently in so many places and so many forms. Not because ancient people were naive, but because they were paying attention. Let us go now to Mesoamerica, where the sun acquired perhaps its most dramatic cultural expression anywhere in the ancient world. The Aztec sun god Tonatiuh was depicted as a fierce, demanding figure, his tongue a sacrificial flint knife, his face radiating energy, his arms spread wide in a posture of hunger. At the center of the famous Aztec sunstone, sometimes called the Aztec calendar Tonatiuh, appears surrounded by glyphs representing the 4 previous suns, 4 previous worlds each destroyed by a different catastrophe. The Aztec cosmology held that the current world was the 5th sun, and it had been created through the self-sacrifice of 2 lesser gods who threw themselves into a divine fire to become the sun and moon. This present sun, this 5th sun, was therefore already a borrowed light. It had been purchased with sacrifice, and it would last only as long as it was repaid. This was not purely metaphor. The Aztec state conducted elaborate regular ritual sacrifices, many of them specifically connected to solar renewal. The dedication of the great temple of Tenochtitlan in 1487 reportedly involved the sacrifice of thousands of people over several days. Whatever we make of that, and we should make of it exactly what it is, which is a devastating use of political and religious power, the underlying impulse came from a genuine, sincere terror that without the right actions, the sun would stop. Interestingly, the Aztec astronomers were among the most precise in the ancient world. Their solar calendar, the Xiuhpohualli, contained 365 days, with a correction system that kept it aligned with the actual solar year. They tracked Venus with extraordinary accuracy. They predicted eclipses. They were not mythologizing because they lacked data. They were mythologizing and collecting data simultaneously, because for them, as for all ancient cultures, the 2 activities were not in conflict. Across the Pacific and Japan, the sun goddess Amaterasu occupied the highest position in the Shinto pantheon. The Emperor of Japan was and technically still is, according to the imperial mythology, a direct descendant of Amaterasu. The rising sun on the Japanese flag is not decoration. It is cosmology made textile. In Norse mythology, the sun was personified as the goddess Sol, who drove the solar chariot across the sky, while being chased by the wolf Skull. It was said that at Ragnarok, the wolf would finally catch her and swallow her. The sun would go dark, and then somehow a new sun would rise, Sol's daughter taking her mother's place, beginning the cycle again. Death and rebirth, chaos and order, darkness and light. These themes appear in solar mythology everywhere on Earth, in cultures that had no contact with each other, because they are describing something real. The sun does disappear each night. The seasons do bring periods of dimness and cold that genuinely threaten life. The pattern of loss and return is not invented, it is observed. The gods and monsters are the clothing that observations wear when the language of physics does not yet exist. There is a moment in the history of science when the sun begins to change from a divine presence to a natural phenomenon, still astonishing, still overwhelming, but subject to measurement, to calculation, to the laws that govern matter everywhere. That moment arrives gradually, not suddenly. It does not wipe away the older understanding so much as it grows alongside it. One of the earliest steps in that transition came from an unlikely direction. shadows. Eratosthenes of Cyrene, a Greek scholar working in Alexandria around 240 BCE, noticed something simple. On the summer solstice at noon, a vertical stick in the city of Cyane, roughly where modern Aswan stands, cast no shadow. The sun was directly overhead. But in Alexandria, several hundred miles to the north, a vertical stick at the same moment cast a measurable shadow. If the earth were flat, both sticks should behave the same way. The fact that they didn't meant the earth's surface was curved, and from the angle of that shadow, approximately 7 degrees, Eratosthenes calculated the circumference of the earth. His result was within a few percent of the modern measurement. He did this with a stick in geometry, and in doing so, he demonstrated something profound. The sun's behavior when measured carefully tells you something exact about the world. It is not a story. It is a measurement. It is a door. That door, once opened, would take 2,000 more years to walk through fully, but it was opened, and every generation of careful watchers who came after the Islamic astronomers of the medieval period, the Renaissance mathematicians, the 17th century telescope builders walked a little further through it, carrying the light with them. What is it about the sun? Do you think that made it the center of so much human meaning for so long? Is it simply that it is the source of warmth and life? Or is there something else, something about its reliability, its daily promise, the fact that it comes back every morning, no matter what happened in the night? The sun does not remember your worst days. It does not carry grudges. It returns with the same light it offered yesterday and the day before, and it will return with that same light long after every human question about it has been asked and answered and forgotten. Maybe that is what made it divine in so many different languages, in so many different centuries. And maybe as we are about to discover, the scientific answer to what makes it shine is even more remarkable than any of the stories we told about it. Because the truth of the sun is not smaller than the myths. It is stranger and deeper, and in its own way just as beautiful. The transition from mythology to science did not happen in a single moment of revelation. It happened through one of the longest, most contentious, and most ultimately humbling debates in the history of human thought. A debate between geologists reading ancient stone and physicists calculating the mathematics of heat. A debate that dragged on for decades before a completely unexpected discovery settled it in a way that neither side had anticipated. That debate is where we are going now. That debate between geologists reading ancient stone and physicists calculating the mathematics of heat is one of the most dramatic intellectual collisions in the entire history of science. And at the center of it stood one of the most brilliant, most confident, and most famously wrong men who ever lived. His name was William Thomson, and the world knew him as Lord Kelvin. Picture the year 1862. The American Civil War is raging. Darwin has published On the Origin of Species just 3 years earlier, and the scientific world is still trembling from the impact. James Clerk, Maxwell, is quietly working on the equations that will unify electricity and magnetism. The Industrial Revolution is reshaping Britain from the inside out, coal smoke over every city. Steam engines rewriting what human labor means. Railways stitching together a continent at speeds that would have seemed miraculous to any previous generation. Into this world of accelerating discovery, Lord Kelvin published a paper titled On the Age of the Sun's Heat. It was precise. It was mathematical. It was written with the kind of calm authority that comes from a man who has spent decades being right about difficult things. And its conclusion was stark. The sun Kelvin calculated could not be older than approximately 20 to 40 million years. Perhaps 100 million at the absolute outside limit of generosity. To most people in 1862, that seemed almost incomprehensibly ancient. 20 million years. But to the geologists and biologists who were beginning to read the deep record of the Earth, it was a problem, a serious one. To understand why Kelvin reached that number, you have to understand what he was working with. By the mid-19th century, physicists had developed the laws of thermodynamics with extraordinary rigor. They understood that energy could neither be created nor destroyed, only transformed. They understood that heat flows from hot to cold, always without exception. They had measured the sun's energy output with reasonable precision, and they knew that any source of energy, any fuel eventually exhausts itself. The question was simply, what was the fuel and how long could it last? Chemical combustion, the burning of fuel in the conventional sense, had already been ruled out, as we touched on before. But Kelvin and Helmholtz had proposed an alternative that seemed physically impeccable: gravitational contraction. The sun, they suggested, was slowly collapsing under its own weight. As the outer layers fell inward, they compressed, and compression generates heat. This is the same principle that makes a bicycle pump warm when you use it. You are compressing air, and compression converts mechanical energy into thermal energy. A contracting sun would continuously convert gravitational potential energy into radiated light and heat. It would shrink almost imperceptibly, perhaps a few tens of meters per year, far too small to detect from Earth. But over millions of years, this process could sustain the sun's observed luminosity without any exotic fuel required. Kelvin's calculation was not careless. He used the best physics available. He accounted for the sun's mass, its radius, its measured energy output. He was meticulous, and the answer he got was 20 to 40 million years, a figure that seemed generous enough to accommodate most biological and geological processes, even if it made some geologists uncomfortable. It would turn out to be off by a factor of more than 100. Now let's hear the other side of this debate. Because while Kelvin was publishing his calculations, the geologists were not staying quiet. Charles Lyell, the father of modern geology, had spent decades reading the story, written in rock layers and erosion patterns and the slow accumulation of sediment on ocean floors. His principle of uniformitarianism, the idea that the geological processes we observe today have been operating at roughly the same rates throughout Earth's history, implied an Earth of staggering age, not millions of years, hundreds of millions, possibly more. When Darwin published his theory of evolution by natural selection, he needed geological time too. Natural selection is a slow accumulative process. The diversity of life on Earth, the branching, the specialization, the vast variety of forms adapted to vast variety of conditions, required time on a scale that made Kelvin's numbers deeply uncomfortable. Darwin himself calculated that the erosion of a particular geological formation in southern England, the Weald, would have required approximately 300 million years at observed erosion rates. That was already 7 times Kelvin's upper limit for the age of the sun. Other geologists were finding similar deep time scales embedded in the rock record everywhere they looked. Salt concentrations in the oceans. If you assumed that rivers had been carrying salt into the sea at roughly current rates, implied an Earth hundreds of millions of years old. The sheer thickness of sedimentary rock formations, deposited grain by grain over unimaginable spans of time, told the same story. The Earth was ancient, profoundly, almost unimaginably ancient. And if the Earth was ancient, the sun had to be ancient too, because the sun has been there for every day of Earth's history. Whatever lit the sky above the first oceans, the first continents, the first living cells, it was the same sun that rises now. Here is what makes this debate so fascinating from the perspective of how science actually works. Both sides had legitimate evidence. Both sides were reasoning carefully from real observations. Neither side was simply making things up or wishfully thinking. Kelvin had physics. The laws of thermodynamics were solid. Gravitational contraction was a real mechanism. His mathematics was sound. The problem was not that his reasoning was wrong, it was that it was complete within a framework that was itself incomplete. The geologists and biologists had observation. The rock record was real. Evolution was real. The timescales implied by careful measurement of natural processes were real. They could not produce a mechanism for the sun's energy that was Kelvin's domain, but they could read the evidence of deep time in the world around them with growing confidence. When evidence from 2 different fields of science appears to contradict, there are a few possibilities. One side might simply be wrong. Both sides might be wrong in different ways. Or, and this is the possibility that feels most exciting in retrospect, neither side is fully wrong, and the contradiction is pointing towards something that neither side has yet imagined. In this case, it was the third option. And what neither side had imagined was sitting inside the atom, invisible to every instrument, then available waiting to be discovered by a woman working in a Paris laboratory with radioactive materials that no one yet understood. Let us spend a moment with Kelvin himself, because he deserves more than a dismissal. William Thomson, he became Lord Kelvin in 1892, was one of the most productive scientists of the 19th century. He made foundational contributions to thermodynamics, to electromagnetism, to the physics of heat conduction. He played a central role in the successful laying of the first transatlantic telegraph cable, a project so complex and so audacious that it required solving problems no one had solved before. He held more than 70 patents. He invented instruments that are still conceptually in use today. He was by any measure brilliant, and he was absolutely stubbornly publicly certain about the sun's age until almost the end of his life. In 1897, when the evidence for radioactivity was beginning to accumulate, and some physicists were quietly suggesting it might change the energy calculation, Kelvin dismissed the idea. In 1900, when he gave his famous Baltimore lectures at Johns Hopkins University, lectures that otherwise stand as a monument of physical insight, he maintained his position on the sun's age. He was 82 years old. He had been wrong for nearly 4 decades on this particular question, and he did not know it yet. He died in 1907. The full explanation of nuclear fusion, the real answer to what powers the sun, would not come for another 3 decades. He never knew he was wrong, and in a strange way that might be the most human part of his story. We are all of us working with incomplete frameworks. Every generation is. The frameworks we have feel complete from the inside. They explain what needs explaining. They make predictions that come true, often enough to build confidence they have the weight of many verified successes behind them. It is genuinely difficult from inside a working framework to imagine what the framework cannot see. Think about this for a moment. Is there something you are currently certain about, some explanation for how things work? Some model of a person or a situation or a field of knowledge that feels solid and well supported, but might be built on an assumption you haven't yet examined. Kelvin's assumption was that all energy sources were already known, that the periodic table was essentially complete, that atoms were indivisible and inert, that everything that mattered had been discovered, and what remained was simply precision work, calculating to more decimal places. He was not alone in this belief. Lord Rayleigh, another towering figure of Victorian physics, is sometimes quoted as saying that the future of physics lay in measurements of the 6th decimal place. The great edifice of classical physics seemed complete. The windows were all in. The roof was on. What remained was interior decoration. And then in 1895, Wilhelm Röntgen discovered X-rays. The following year, Henri Becquerel discovered that uranium spontaneously emitted rays of its own, without any external energy source, without any chemical reaction, with no obvious cause at all. The following year after that, a young Polish physicist named Marie Curie began her doctoral research on Becquerel's mysterious rays. She named the phenomenon radioactivity. And the framework that had seemed so complete, so beautifully finally complete, cracked open like a seed. Radioactivity was in the context of everything 19th century physics believed almost impossible. Here was matter that produced energy continuously, not from burning, not from chemical reaction, not from any mechanism that thermodynamics could account for, simply radiating energy out of itself, apparently from nothing. It wasn't from nothing, of course. But understanding what it was actually from required dismantling the atom itself, which required equipment and conceptual tools that didn't yet exist and which would take another generation of physicists to develop. Ernest Rutherford in Manchester, Niels Bohr in Copenhagen, Albert Einstein in Bern writing miracle papers in 1905, James Chadwick discovering the neutron in 1932. each one adding a piece to the picture that Becquerel's mysterious rays had demanded someone paint. But in the last years of the 19th century, what radioactivity represented more than anything else was an announcement, a signal from the universe that there was more, that the map was not complete, that the confident, elegant, mathematically beautiful framework of classical physics had encountered something it could not explain. And rather than stretching to accommodate it, the framework would eventually need to be rebuilt from deeper foundations. For the question of the sun, this mattered in a specific and immediate way. If atoms could release energy spontaneously, if matter contained within itself some reservoir of energy that chemistry and gravity had never suspected, then perhaps Kelvin's entire calculation was built on the wrong assumption. Perhaps the sun's fuel was not gravitational collapse. Perhaps it was something stranger, something smaller, something that lived in the nucleus of the atom itself. George Darwin, Charles Darwin's son and a distinguished scientist in his own right, wrote to Lord Kelvin in the early 1900s, suggesting that radioactivity might resolve the conflict between geological deep time and Kelvin's solar age calculations. If radioactive decay could produce significant heat, then perhaps the Earth was older than Kelvin thought. And if the sun contained similar processes, then perhaps it too was far older than the Kelvin-Helmholtz contraction could explain. Kelvin was not persuaded. He remained convinced that radioactivity was an interesting but ultimately peripheral phenomenon, something that added a little time here and there, but did not fundamentally change the picture. He was wrong. Radioactivity was not peripheral. It was the first crack in a wall that would eventually reveal an entire universe of nuclear energy hiding behind the elegant, confident, apparently complete physics of the 19th century. And it was that crack, that single strange, apparently minor observation of uranium emitting rays, for no chemical reason that set in motion the chain of discovery that would, within half a century, answer the question of the sun's energy source completely permanently, and in a way that Lord Kelvin, for all his brilliance, could not have imagined. The atom was not indivisible. It was not inert. It was not a small, hard, featureless ball of matter. It was an architecture, a structure, a tiny world with its own interior dense and concentrated at the center, mostly empty space held together by forces no one had yet named. And inside that architecture, something astonishing was waiting. Something that would turn out to be the engine of every star in the universe. What that engine is and how it was finally understood is the story that begins right now. In 1905, a 26-year-old patent clerk in Bern, Switzerland, wrote 5 papers in a single year. Any one of them would have made a career. Together, they rewrote physics from the ground up. His name, of course, was Albert Einstein. And buried inside the shortest of those 5 papers, barely 3 pages long, was a single equation that would eventually answer the question of the sun more completely than any calculation Lord Kelvin had ever attempted. The equation was E equals mc squared, and the story of what it actually means and how it connects to that burning fire 4.5 billion years old is one of the quietest, most astonishing stories in all of science. Let's begin not with Einstein, but with a woman in a cold, leaking shed in Paris. Because before E equals mc squared could mean anything for the sun, someone had to crack open the atom itself. And the person who did that, more than anyone else, who gave the world the word radioactivity, who discovered 2 new elements, who won the Nobel Prize twice in 2 different sciences, an achievement no one has replicated since, was Marie Curie. Born Maria Sklodowska in Warsaw in 1867, Curie grew up in a Poland under Russian occupation, where women were barred from attending university. She made a private arrangement with her sister. Each would work to support the other's education in turn. Marie worked as a governess for years, sending money to her sister, studying medicine in Paris, waiting for her own turn. When it finally came, she arrived in Paris in 1891 at 24 years old, with almost no money, living in an attic apartment so cold that water froze in the wash basin overnight, and she threw herself into physics with an intensity that her professors found startling. She discovered polonium named after her occupied homeland and radium. She built instruments to measure the invisible rays being emitted by uranium, and she measured them with a precision no one had achieved before. She worked in a converted shed that her colleagues acknowledged was, by the standards of European university laboratories, embarrassingly inadequate. The shed leaked. It was cold in winter and hot in summer. The radioactive materials she handled daily were slowly and visibly destroying her health. She would die of aplastic anemia in 1934, almost certainly caused by decades of radiation exposure. And what she found in that shed with those instruments changed everything. Radioactivity, the spontaneous emission of energy from the nucleus of certain atoms, violated the first principle of 19th century thermodynamics as it had been understood. Here was matter, producing energy with no apparent input, no chemical reaction, no external trigger. The uranium simply sat there and radiated. The radium glowed faintly in the dark of the laboratory, cool to the touch, producing energy hour after hour, year after year, without diminishing in any way that early instruments could detect. Where was the energy coming from? Ernest Rutherford, working first in Montreal and then in Manchester, was the next crucial figure. Rutherford was a New Zealander, large, loud, physically imposing, fond of singing, onward Christian soldiers, while working and possessed of an almost supernatural physical intuition about the behavior of matter at scales too small to see. He took Curie's radioactivity and began systematically dismantling the atom to understand it from the inside. In a famous experiment in 1911, Rutherford's team fired alpha particles, tiny positively charged fragments, ejected from radioactive atoms at an extremely thin sheet of gold foil. The prevailing model of the atom at the time was J.J. Thomson's plum pudding model, a diffuse cloud of positive charge with electrons embedded in it like raisins in a cake. If that model were correct, the alpha particles should pass through the gold foil with at most slight deflections like cannonballs fired through a fog. Instead, some alpha particles bounced almost straight back. Rutherford described his astonishment famously. It was as if you fired artillery shells at tissue paper, and they came back and hit you. What the results revealed was that the atom was almost entirely empty space, with a tiny, incredibly dense, positively charged nucleus at the center. The nucleus was roughly 100,000 times smaller than the atom itself. If the atom were the size of a football stadium, the nucleus would be a marble on the 50-yard line. Almost everything you are made of is empty space. The solidity of the chair beneath you, the floor beneath that, the ground beneath the building, it is an illusion produced by electromagnetic forces, not by matter actually occupying space in the way that everyday experience suggests. And inside that tiny, dense, almost impossibly small nucleus, that marble in the center of the stadium, lived a concentration of energy that nothing in chemistry or classical physics could have predicted. Now we can return to Einstein. Because it was Einstein who gave the mathematical language to what Curie and Rutherford were finding experimentally. E equals mc squared. Energy equals mass times the speed of light squared. Let's sit with this for a moment, because it is easy to say quickly and hard to really feel. The speed of light is approximately 300 million meters per second. That is already a number that resists imagination. Light can circle the entire Earth 7.5 times in a single second. Squared that number becomes 90 quadrillion, 9 followed by 16 zeros. What Einstein's equation says is that mass and energy are not different things. They are the same thing expressed differently. Mass is frozen energy. Energy is liberated mass. And the exchange rate between them, the conversion factor, is the speed of light squared, which is an almost incomprehensibly large number. This means that even a tiny amount of mass converted entirely to energy produces an almost incomprehensibly large amount of energy. 1 gram of mass, about the weight of a small paperclip, if converted entirely to energy, would produce approximately 90 terajoules. That is roughly equivalent to the energy released by 21,000 tons of TNT from 1 paperclip. The sun, of course, is not made of paper clips, but the principle is the same. If the sun could convert even a small fraction of its mass into energy through some process more efficient than chemical combustion, it could shine for billions of years, not millions. The question was not whether E equals mc squared was right. The question was, what process inside the sun was actually doing the conversion? That question could not be answered until the nucleus of the atom was understood well enough to imagine what happened when two nuclei came close together under extreme conditions. And that understanding came slowly through the work of many people across 2 decades that also happened to contain a world war, an economic collapse, the rise of fascism, and the first steps toward weapons that would use this same principle to do something very different from lighting up a sky. James Chadwick discovered the neutron in 1932, the neutral particle inside the nucleus that had been suspected but never confirmed. With the neutron, the structure of the atom finally made sense. The nucleus contained protons positively charged and neutrons electrically neutral. They were held together by a force that no one had yet named a force stronger than electromagnetism, operating only at the tiny scales of the nucleus itself, the strong nuclear force. And here is where the picture of the sun begins to sharpen. Two protons, both positively charged, repel each other electrically. Under normal conditions, the conditions of chemistry of everyday matter, of every temperature and pressure on the surface of the Earth, they will never get close enough to interact via the strong nuclear force. The electromagnetic repulsion keeps them apart. This is why nuclear fusion does not happen at room temperature. This is why you can hold hydrogen gas in a balloon without it spontaneously fusing into helium and releasing a burst of nuclear energy. But under extreme conditions, temperatures in the tens of millions of degrees pressures, millions of times higher than Earth's atmosphere, protons can be forced close enough together that the strong nuclear force takes over. And when it does, something remarkable happens. The protons merge, they combine. And in combining, they lose a tiny fraction of their original mass. Not much. About 0.7%. Less than 1% of the mass of the original particles simply vanishes from matter entirely. And according to E equals mc squared, that vanished mass reappears as energy, pure radiant world-illuminating energy. This is nuclear fusion. This is what the sun is doing. And the conditions required for it, those extreme temperatures and pressures, exist naturally in exactly one place in our solar system, the core of the sun. It is worth pausing here to appreciate how strange this is. The energy that warmed your face today, that grew the food you ate, that powers the weather patterns, that brought whatever sky you woke up under, that energy came from mass, from actual matter that no longer exists as matter. It was converted inside the sun in reactions happening right now, as we speak, from the substance of hydrogen atoms into pure energy and radiated outward across 93 million miles of space to reach you. You are, in a very literal sense, powered by the conversion of mass into energy inside a nuclear furnace. Every photon of sunlight that has ever touched your skin was born from a small disappearance, a tiny subtraction from the sum total of matter in the universe paid out as light. E equals mc squared is not an abstract mathematical statement. It is a description of something that is happening continuously right now in the heart of the star above you. Now let us trace the path from Einstein's equation to the actual understanding of how the sun fuses hydrogen into helium, because that final step required one more piece, and it came from a source that highlights something important about how scientific discovery actually happens. The problem with nuclear fusion, even after Chadwick's discovery of the neutron and the basic understanding of nuclear structure, was a quantum mechanical one. The temperatures at the sun's core, approximately 15 million degrees Celsius, are extremely high by any everyday standard, but they are not, strictly speaking, high enough for protons to overcome their electromagnetic repulsion classically. If you calculate the energy of a typical proton at 15 million degrees and compare it to the energy barrier it would need to clear to get close enough to another proton for fusion, the numbers don't quite work. The protons should not be able to fuse. The sun should not shine as brightly as it does. This was a genuine puzzle in the 1920s, when astrophysicists first began seriously applying nuclear physics to stellar energy. And the resolution came from a phenomenon called quantum tunneling. In quantum mechanics, particles do not have precisely defined positions and momenta the way billiard balls do. They are described by probability distributions, wave functions that spread out in space. And one of the consequences of this spreading is that a particle has a small but real probability of appearing on the other side of an energy barrier without having enough energy to cross it classically. It tunnels through the barrier in the language physicists use for this phenomenon. In the sun's core, the vast majority of proton encounters result in simple repulsion. The protons approach, push back, fly apart. But a tiny fraction, an almost unimaginably small fraction tunnel through the barrier. And because the sun contains approximately 1.2 times 10 to the 57th protons, even a vanishingly small probability applied to an enormous number of particles produces an enormous rate of fusion reactions. The sun does not shine because every proton fuses easily. It shines because it has so many protons that even the near impossible happens constantly. George Gamow, a Ukrainian-born physicist working in the late 1920s, was the first to apply quantum tunneling to nuclear physics in this way. He was 24 years old. He had escaped the Soviet Union in a remarkable adventure involving a kayak the Black Sea and several close calls that belong in a different kind of story. He brought his tunneling calculations to Niels Bohr in Copenhagen, and Bohr immediately grasped their significance for stellar physics. The theoretical framework that followed, developed in 1939 by Hans Bethe, a German-born physicist who had fled Nazi Germany and was then working at Cornell, described the specific chain of reactions by which hydrogen is fused into helium in a sun-like star. Bethe worked out the mathematics with extraordinary precision. He showed not only that fusion could power the sun, but that it could do so at exactly the rate needed to match the sun's observed luminosity for a duration consistent with the geological and biological timescales that had tormented Lord Kelvin's calculations for decades. The debate that had begun in the 1860s was over. The geologists were right, the Earth was old, the sun was old, and the energy source was something no one in the 19th century had been equipped to imagine the conversion of mass into energy happening proton by proton nucleus by nucleus in the 15 million degree furnace at the star's center. Bethe was awarded the Nobel Prize in Physics in 1967 for this work. He lived to be 98 years old, long enough to see the first direct detection of the particles neutrinos produced in the very fusion reactions he had described mathematically in 1939. The theory and the observation matched almost perfectly. Here is the detail that stays with me in all of this. The journey from Becquerel, noticing that uranium fogged a photographic plate in 1896, to Bethe writing down the equations for stellar fusion in 1939 took 43 years. It required contributions from dozens of scientists across multiple countries and multiple generations. It required two independent streams of discovery, experimental physics and theoretical physics, running in parallel, sometimes in contact, sometimes not gradually, converging on the same answer from different directions. No single person could have done it alone. No single discipline could have done it alone. The answer required chemistry, thermodynamics, electromagnetism, quantum mechanics, nuclear physics, and astrophysics to be developed and then integrated across a span of decades. And the answer, when it finally came, was this: the sun shines because matter and energy are the same thing, and because the conditions at the sun's core are extreme enough and the sun large enough to allow the exchange between them to happen at a rate sufficient to light up a solar system for billions of years. Simple, profound, and waiting inside the atom, the whole time patient and silent for someone to ask the right question in the right way at the right moment. The question now is, what exactly happens in that core? What is the actual sequence of reactions, step by step, from hydrogen to helium? What does it feel like, if anything can feel like anything at that scale, to be a proton in the heart of a star? That is exactly where we are headed next. Right now, at this very moment, something is happening at the center of the sun that has been happening every single second for 4.5 billion years. It happens in a space roughly the size of Jupiter. It happens at a temperature of 15 million degrees Celsius. And it happens so slowly, so patiently, so quietly at the individual particle level that a single proton might wait 9 billion years before it participates. 9 billion years. Longer than the current age of the universe. And yet the sun shines brilliantly every day. The numbers, when you hold them together, are almost too strange to believe. Let us go there. Let us go to the core of the sun. Imagine descending through the sun's visible surface, the photosphere, that churning golden layer we see from Earth, and continuing inward. The temperature climbs immediately. The light you pass through at the surface, around 5,500 degrees Celsius, gives way to something beyond any scale that Earth provides a reference for. 100,000 kilometers down. 200,000. You are moving through plasma, not gas, not liquid, not solid, but a fourth state of matter in which electrons have been stripped entirely from their atoms, leaving bare nuclei moving at extraordinary speeds through a sea of charged particles. The pressure climbs with you. At the surface, solar pressure is already formidable. But as you descend toward the core, the innermost 25% of the sun's radius, roughly the region where nuclear burning takes place, the pressure reaches approximately 250 billion times Earth's atmospheric pressure at sea level. That is the weight of the entire sun pressing inward. 696,000 kilometers of plasma above you, all of it pulling downward through gravity, all of that weight focused on this central region. And in that region, that compressed, searingly hot, impossibly pressured core hydrogen nuclei are doing something they cannot do anywhere else in the solar system. They are fusing. The process is called the proton-proton chain. It is the dominant energy source in stars of the sun's size and smaller, and it proceeds in steps, each one releasing a small amount of energy, each one building toward a final product that is chemically, structurally, fundamentally different from the ingredients that went in. The first step, 2 protons, 2 bare hydrogen nuclei, each carrying a single positive charge, collide with enough velocity, and through quantum mechanical tunneling, they fuse. But 2 protons cannot simply stick together as 2 protons. The strong nuclear force alone cannot hold a nucleus of 2 protons stably. The electromagnetic repulsion between them would eventually overcome it. For the fusion to produce a stable product, one of the protons must transform through a process called beta plus decay. Mediated by the weak nuclear force, one proton converts into a neutron. In doing so, it releases a positron, the antimatter counterpart of an electron, and a neutrino, an almost massless, nearly undetectable particle that will travel outward from the core and reach Earth in approximately 8 minutes, passing through your body right now at a rate of tens of billions per second, as though you were not there at all. The result of this first step is a nucleus containing 1 proton and 1 neutron. This is deuterium-heavy hydrogen. And the energy released in this step, combined with what comes next, is what ultimately powers the light you see. Pause here, because the neutrino detail is worth dwelling on for a moment. Right now, tens of billions of neutrinos produced in the sun's core are passing through every square centimeter of your body every second. They are produced in the very first step of the proton-proton chain, the fusion reaction happening at the sun's center right now as you listen. They travel outward from the core at nearly the speed of light. They pass through the entire body of the sun, through hundreds of thousands of kilometers of dense plasma that stops virtually every other kind of particle as easily as light passes through air. They cross 93 million miles of space. They reach Earth. They pass through the entire planet. They pass through you. You are being penetrated by the direct products of nuclear fusion happening in the sun's core continuously right now. Not the light, the light's journey is a completely different story. The neutrinos, the raw immediate output of the reaction itself. In the 1960s, physicist Raymond Davis Jr. built a detector in the Home State Gold Mine in South Dakota, a tank containing 100,000 gallons of cleaning fluid buried deep underground to shield it from cosmic rays. He was trying to catch solar neutrinos. The detector worked by waiting for the rare event in which a solar neutrino interacted with a chlorine atom and converted it to a radioactive argon atom that could be chemically extracted and counted. The experiment ran for decades. It caught neutrinos, but it only caught about 1/3 as many as theoretical models of the sun predicted. This discrepancy, known as the solar neutrino problem, troubled physicists for 30 years. Was the model of solar fusion wrong? Was the detector wrong? Was something happening to the neutrinos on their way from the sun to Earth? It turned out to be the third option. Neutrinos come in three types: electron neutrinos, muon neutrinos, and tau neutrinos. The sun produces electron neutrinos, but as they travel, they oscillate, they shift between types, cycling through all three as they move through space. Davis's detector could only catch electron neutrinos, and by the time the solar neutrinos arrived, many had transformed into the other types. When newer detectors were built that could catch all three types, the numbers matched theoretical predictions perfectly. The sun was right. The physics was right. Neutrinos simply do something stranger than anyone had anticipated. Davis received the Nobel Prize in Physics in 2002 for his work. And the solar neutrino problem, once solved, gave us something unexpected: the first direct experimental evidence that neutrinos have mass. However slight a discovery that opened an entirely new chapter in fundamental particle physics, all from a tank of cleaning fluid buried in a gold mine in South Dakota. Back to the core, back to the proton-proton chain. The second step. The deuterium nucleus produced in step 1 collides with another free proton. This fusion is considerably faster than the first step. It happens in roughly 1 second, compared to the billions of years a proton might wait for step 1. The deuterium absorbs the proton and becomes helium-3, a nucleus with 2 protons and 1 neutron. This step releases a gamma ray, a photon of extremely high-energy light, born in the furnace of the sun's core, which will begin an extraordinary journey outward. The third step, 2 helium-3 nuclei, each produced by the first 2 steps, collide with each other. They briefly form a beryllium-6 nucleus, but this is unstable. Almost immediately it breaks apart, releasing 2 free protons back into the plasma protons that can begin the cycle again, and leaving behind 1 helium-4 nucleus. 2 protons and 2 neutrons bound together by the strong nuclear force, stable and complete. The net result of the entire proton-proton chain, 4 hydrogen nuclei, have become 1 helium-4 nucleus. And in that transformation, approximately 0.7% of the original mass has been converted through E equals mc squared into energy, mostly gamma rays, plus neutrinos, plus the kinetic energy of the particles themselves, which heats the surrounding plasma. Every second, the sun converts approximately 600 million tons of hydrogen into helium through this process. And in that conversion, approximately 4 million tons of mass, 4 million tons of actual matter, are transformed into pure energy. 4 million tons every second vanishing from material existence and reappearing as light, as warmth, as the energy that drives everything alive on this planet. Now step back from the individual reaction and look at the whole picture, because the scale of what is happening deserves to be felt, not just stated. The sun contains approximately 70% hydrogen by mass, that is the fuel. Over its 4.5 billion year life, it has converted perhaps 4% of its total hydrogen into helium through fusion. Not 4% of the core's hydrogen, 4% of the entire sun's mass in hydrogen. The sun is so large that even after 4.5 billion years of burning at this rate, It has barely made a dent in its available fuel. This is why the sun can last for 10 billion years total, roughly another 5 billion years from now. Not because it burns slowly in absolute terms, 4 million tons per second is not slow, but because it started with an amount of fuel so vast that 4 million tons per second barely registers. Compare this to what Kelvin calculated. Gravitational contraction could power the sun for perhaps 20 to 40 million years. Nuclear fusion powers it for 10 billion. The difference is not a matter of degree. It is a factor of 200 to 500. The real energy source was not slightly more powerful than what Kelvin imagined. It was in a completely different category of existence. There is something else worth understanding about the proton-proton chain that often gets lost in simplified explanations. The reaction is astonishingly inefficient at the individual particle level, and that inefficiency is precisely what makes the sun stable. The rate-limiting step is that very first fusion event where two protons must collide and one undergoes beta plus decay. This event is so improbable that any given proton in the sun's core may wait on average about 9 billion years before it undergoes this reaction. The sun is currently about 4.5 billion years old. Many of the protons in the core have not yet fused even once. Why does this matter? Because it means the sun is not burning out of control. It is burning at a rate set by the extreme improbability of that first step. The sun is in a very real sense self-regulated. If the core temperature rises slightly, if the reactions speed up even a little, the increased pressure pushes the outer layers outward. The core expands slightly. The temperature drops back down, and the rate returns to equilibrium. If the rate decreases, the core contracts, heats up, and the rate increases again. This feedback mechanism, hydrostatic equilibrium, is the reason the sun has been burning at almost exactly the same rate for billions of years. Not because some external force controls it, but because the physics of a self-gravitating ball of plasma naturally produces a stable operating point. The sun is a thermostat, an ancient nuclear self-regulating thermostat, 4.5 billion years old, running with a steadiness that no human engineering has ever approached. There is a common misconception worth addressing here. Many people assume that having a nuclear reactor this close to Earth is somehow precarious, that a small change in conditions might cause it to flare up catastrophically or suddenly burn much hotter. The opposite is closer to the truth. The sun's stability comes precisely from the physics of its own structure. Sudden increases in fusion rate push the sun outward and cool the core, slowing the rate back down. Sudden decreases allow the sun to contract, heating the core and speeding the rate back up. The sun does have variations, the 11-year sunspot cycle periods of slightly higher or lower magnetic activity that can disrupt satellite communications and produce auroras. But these variations involve the outer layers of the sun, not the core. The core fusion rate is by any standard that humans would call stable, extraordinarily constant. Do you ever wonder about the stars you can see on a clear night, whether they too are doing this same thing? Quietly fusing, self-regulating, ancient and patient. Most of them are. The vast majority of stars visible to the naked eye are main sequence stars, burning hydrogen into helium through variants of the same proton-proton chain, each one a nuclear furnace calibrated by its own mass and gravity. Each one steady in ways that human technology has never replicated. Here is a thought I find quietly extraordinary, and I want to offer it before we move on. The proton-proton chain that powers the sun is, as far as we know, the dominant energy source for the majority of stars in the observable universe. When you look up at the night sky and see those quiet scattered lights, ancient, indifferent, impossibly far away, you are looking at nuclear furnaces. Every one of them. Every steady point of light, a world of plasma held together by its own gravity, fusing light elements into heavier ones, converting mass into light at a rate determined by the slow improbability of quantum tunneling. And one of them, one specific middle-aged, thoroughly unremarkable G-type main sequence star, happens to be close enough to a small rocky planet for that light to warm an ocean power, a weather system, feed a biosphere, and make its way eventually to you tonight in the form of the energy that grows the food that keeps you breathing. Does knowing what is actually happening out there make the night sky feel smaller or larger? I think it makes it larger, more strange, more present, more alive. The gamma rays born in that 15 million degree core, each one produced by a helium nucleus, snapping into existence, now begin a journey outward. A journey so slow, so tortured, so counterintuitive that it redefines what it means for light to travel through matter. The energy that left the core of the sun does not reach the surface in 8 minutes. It does not reach the surface in 8 years or 8 centuries. The journey from core to surface, a distance of about 500,000 kilometers, which light in empty space could cross in under 2 seconds, takes on average somewhere between 100,000 and 1 million years. And understanding why, understanding what happens to a photon born in the sun's nuclear furnace as it attempts to make its way to the surface, is one of the most beautiful and counterintuitive stories in all of astrophysics. A story of a wanderer born in unimaginable heat, spending an eternity finding its way out, and then crossing the distance between a star and a planet in the time it takes you to make a cup of tea. That wanderer's story is where we go next. The sunlight touching your skin right now is old, not 8 minutes old the way most people assume. The energy carried in that light, the actual energy, was generated in the sun's core somewhere between 100,000 and 1 million years ago. It has been wandering, trapped, bouncing, absorbed, re-emitted, redirected, and absorbed again for longer than modern humans have existed on this planet, before it finally broke free of the sun's surface and flew across 93 million miles of empty space to reach you in just over 8 minutes. One photon. 100,000 years inside the sun. 8 minutes to reach your face. That contrast, that staggering difference in time scales, is the story of this part of our journey tonight. To understand why a photon born in the sun's core takes so extraordinarily long to escape, you have to understand what the interior of the sun is like as a medium for light to travel through. And it is nothing like the vacuum of space where light travels at its full speed, approximately 300,000 kilometers per second, in an essentially straight line meeting, almost nothing on its way. The sun's interior is plasma. Dense, hot, churning plasma. And plasma, particularly at the pressures and temperatures found in the sun's radiative zone, the thick shell surrounding the core, extending from about 25% of the sun's radius to about 70%, is almost perfectly opaque to light. Not transparent the way glass is, not translucent the way fog is. Opaque in the way that a wall is opaque, except that this wall is made of ionized gas at millions of degrees, and it extends for hundreds of thousands of kilometers in every direction. A photon produced in a fusion reaction at the sun's core is born as a gamma ray, extremely high-energy light far beyond the visible spectrum. The moment it is born, it begins to travel outward at the speed of light. And within an extraordinarily short distance, scientists estimate the mean free path of a photon in the solar core is somewhere between 1 and a few centimeters. It encounters a particle of the plasma. It is absorbed. It ceases to exist as a photon. And then almost immediately a new photon is emitted in a random direction. This is the key. The absorption and re-emission happens in a random direction. The new photon flies off still at the speed of light, and within another centimeter or a few centimeters, it is absorbed again. And a new one is emitted again, in another random direction, and so on, for hundreds of thousands of years. This process is called a random walk. It is also called, more poetically, a drunkard's walk, the mathematical description of motion that proceeds by random steps with no preferred direction. A particle taking a random walk does not move efficiently toward any destination. It wanders, it backtracks, it loops. It occasionally makes brief progress in one direction before reversing course entirely. There is a mathematical result for random walks that is both elegant and, in this context, almost pitiable. If a particle takes n steps each of length L in random directions, the expected distance it will travel from its starting point is not n times L. That would be the distance if it always went straight. The expected distance is the square root of n times L. What this means for a photon in the sun to travel outward a distance of 500,000 kilometers from core to surface, the photon must take an enormous number of steps. The number of individual absorption and re-emission events is estimated at around 10 to the power of 26. That is a 1 followed by 26 zeros. 10 trillion individual scattering events. And the cumulative result of that staggering number of random steps, each one covering only a centimeter or so, is a journey that takes somewhere between 100,000 and 1 million years. Some models suggest estimates running even longer for energy produced deepest in the core. The order of magnitude is not in doubt. The photon wanders for an almost incomprehensibly long time. Picture it this way. Imagine you were in the center of a vast city, a city made entirely of fog so thick that you cannot see more than an inch in front of you. Every step you take goes in a completely random direction. You have no compass, no map, no memory of where you have been. You walk 1 inch, stop. Walk another inch in a completely random direction, stop. Every step is independent of the one before it. How long would it take to reach the city's edge 500 kilometers away? If you could walk straight at a normal walking pace, it would take roughly a week. But walking randomly, the mathematics of the drunkard's walk says you would need astronomically more steps and astronomically more time to cover the same distance. The photon situation is exactly this. It is not blocked by a wall. It simply keeps being redirected. Every centimeter, a new direction. Every random direction, an equal chance of going inward as outward. And the cumulative statistical patient result of that process, replicated 10 trillion times, is a journey that outlasts the entire history of human civilization by a factor of more than 50,000. There is something else worth understanding about what happens to the photon as it wanders. It does not arrive at the sun's surface as the same photon that was born in the nuclear core. The energy of a gamma ray born in fusion at 15 million degrees is far higher than the energy of the photons that eventually leave the sun's surface as visible light, infrared, and ultraviolet radiation. As the photon is absorbed and re-emitted over and over through hundreds of thousands of years, it interacts with plasma at progressively lower temperatures and densities as it moves outward. Each re-emission produces a photon appropriate for the local temperature of the surrounding plasma. By the time the energy reaches the photosphere, the visible surface where the plasma finally becomes thin enough for photons to escape into space, the temperature is only about 5,500 degrees Celsius, and the photons being emitted at that temperature are no longer gamma rays. They are photons of visible light, infrared radiation, and ultraviolet light. The light you see is not the same light that was born in the nuclear reaction. It is the same energy transformed, thermalized, worn down across billions of interactions, expressed in a form completely different from its violent origin. A gamma ray born in a nuclear explosion at 15 million degrees has been gently worn down over 100,000 years into warm golden light appropriate for a spring afternoon. Now, once a photon finally reaches the photosphere, its situation changes entirely. Suddenly, instead of a dense fog of charged particles absorbing and scattering it at every centimeter, it faces open space. Vacuum, and in vacuum light, travels at its full speed unimpeded in a straight line. From the photosphere to Earth, a distance of approximately 149 million kilometers, takes just about 8 minutes and 20 seconds. After a journey of up to 1 million years inside the sun, the final leg takes less time than most people spend eating breakfast. That 8-minute journey is worth sitting with. It means that when you look toward the sun, you are seeing it as it was 8 minutes ago. You are always looking into the past, even with the nearest star, even with an object you can feel warming your face. And the energy in that light, it left the sun's core long before the first cave paintings were made in France. Long before Neanderthals walked Europe, long before our species evolved on the African savanna, the energy that grew your food, that powers the wind, that evaporates the oceans into clouds, it was generated before humans existed, and it has been traveling toward this moment patiently for all of that time. Here is a question to carry with you. Does it change the feeling of standing in sunlight, knowing that? Knowing that the warmth on your skin has been traveling toward you not for 8 minutes, but for 100,000 years or more. That the journey of that energy through the interior of the sun was longer than all of recorded human history, combined many times over. I think it does change it. Not in a way that makes sunlight feel less immediate or less real, but in a way that makes it feel heavier, more ancient, more earned. There is another layer to the photon story that is rarely discussed outside of technical contexts. Not all parts of the sun's interior transmit energy by this radiative process. In the outer 30% of the sun's radius, a zone called the convective zone, the plasma becomes too opaque even for the slow, radiative random walk to efficiently transport energy outward. Something else takes over. Convection. The same process that makes water in a pot roll and bubble when you heat it from below. Packets of hot plasma rise from the lower boundary of the convective zone, carry their energy upward, cool, as they approach the surface and sink back down, only to be reheated at the bottom and rise again. These convective cells are visible on the sun's surface as granules roughly 1,000 kilometers across, constantly forming and dissolving, giving the photosphere its characteristic textured appearance when viewed through a solar telescope. The largest convective structures, called supergranules, are around 30,000 kilometers in diameter, about 2.5 times the diameter of Earth. They last for a day or two before dissolving and reforming elsewhere. Smaller granules last only about 10 minutes each. The entire visible surface of the sun is in constant churning motion, not random, but organized by the interplay of heat rising from below, and the sun's magnetic field threading through everything. This convection is also the driver of the sun's magnetic activity, the sunspot's solar flares and coronal mass ejections that occasionally send charged particles streaming toward Earth, lighting up auroras at the poles, and in extreme cases disrupting power grids and satellite communications. The sun's magnetic field is generated by the differential rotation of the convective zone. The equator of the sun rotates faster than the poles, winding the magnetic field lines into complex tangles that eventually snap and release energy in ways that are still not fully understood. Above the photosphere, the sun has layers that are in their own way as mysterious as the core. The chromosphere, a thin reddish layer visible only during a total solar eclipse as a flash of color around the moon's silhouette, reaches temperatures of around 20,000 degrees. And above that, the corona, the sun's outer atmosphere, which streams outward millions of kilometers into space, reaches temperatures of 1 to 3 million degrees Celsius. That number deserves to stop you. The sun's surface is 5,500 degrees. Its outer atmosphere is 1 to 3 million degrees. If you moved away from a campfire, you would get colder, not hotter. Yet moving away from the sun's photosphere upward through the chromosphere and into the corona, you get dramatically hotter, by a factor of hundreds. This is called the coronal heating problem, and it has been one of the most stubborn open questions in solar physics for decades. Various mechanisms have been proposed: Alf-Venn waves carrying energy upward from below and depositing it in the corona magnetic reconnection, events releasing stored magnetic energy as heat nanoflares, too small to detect individually, but collectively significant. The Parker Solar Probe, launched by NASA in 2018 and now in an orbit that skims progressively closer to the sun, became the first spacecraft to fly through the corona itself in 2021. The data it is returning is already reshaping our understanding of coronal heating, though the full picture remains an active area of research. The full journey of solar energy then looks like this. Born in a nuclear reaction at the core, wandering in random steps through the radiative zone for anywhere from 100,000 to perhaps 1 million years. picked up by convection in the outer layers and carried upward in rising columns of plasma, released at the photosphere into open space, traveling 8 minutes and 20 seconds across 93 million miles of vacuum, passing through Earth's atmosphere, scattering off molecules arriving at the ground as a mixture of visible light, some ultraviolet, some infrared, and finally resting on your face, on the leaves of a tree, on the surface of an ocean, where it powers evaporation that becomes cloud, that becomes rain, that fills rivers, that carve canyons over millions of years. The photon that began as a gamma ray in a nuclear furnace has become, by the end of its journey, the driver of weather systems, ocean currents, photosynthesis, and life itself. It has been transformed beyond recognition from its violent origin. And yet, the energy is the same energy conserved through every transformation, every scattering, every conversion, until it is finally absorbed by something that uses it, and the chain ends. There is something I find quietly moving about this chain, the way ancient nuclear energy becomes food, becomes thought, becomes the breath of something living. Every photon that has ever warmed a human face was once a gamma ray born in a nuclear furnace old before our species existed. The connection between the sun's core and your skin is not metaphorical. It is physical, direct, unbroken. Across 100,000 years and 93 million miles, and standing in sunlight, eyes closed, feeling that warmth, you are in some real and literal sense receiving a message that was sent before you were born, before your grandparents were born, before every civilization that has ever existed on this planet began its brief, bright story. The sun has been sending that message patiently for 4.5 billion years. Now, the question we have not yet asked tonight, and it is perhaps the most quietly astonishing question of all, is this: how do we actually know any of this? We have never sent a probe to the sun's core. We have never taken a sample of its fuel. Every number we have discussed tonight, the 15 million degrees, the 600 million tons of hydrogen per second, the 100,000-year photon journey, all of it was determined from a distance of 93 million miles using nothing more than the light the sun chooses to send us. That is the story of spectroscopy, of human ingenuity applied to starlight, of a discovery so elegant and so powerful that it turned every star in the universe into a laboratory we could read from Earth. And it begins with a dark line in a spectrum of sunlight that a German lensmaker noticed almost by accident in 1814. A dark line in a spectrum of sunlight. That was where our knowledge of the sun's true nature, its composition, its age, its future, really began. Not in a laboratory, not in an observatory on a mountaintop, in a Munich workshop in 1814, where a glassmaker named Joseph von Fraunhofer was trying to make better lenses. And what he found almost by accident when he passed sunlight through a prism and looked carefully at the resulting rainbow of color was not a smooth, unbroken spectrum. It was a spectrum crossed by hundreds of thin, dark vertical lines. Lines where certain precise colors of light were missing, absent, swallowed before they ever reached his eye. Those lines were a message in a language no one yet knew how to read. But within a few decades, scientists would decode it, and in doing so, they would learn not only what the sun is made of, but what it will someday become. Joseph von Fraunhofer did not know what the dark lines meant. He cataloged them with extraordinary care. He identified more than 500 distinct absorption lines in the solar spectrum, labeling the most prominent ones with letters that physicists still use today: the D lines for sodium, the H and K lines for calcium, the G band for iron and other metals. He measured their positions with a precision that was, by the standards of 1814, almost unbelievable. But he died in 1826 at the age of 39 before the explanation was found. The explanation came in 1859 from the physicist Gustav Kirchhoff and the chemist Robert Bunsen, the same Bunsen whose name adorns the laboratory burner used in chemistry classes around the world. Kirchhoff and Bunsen were studying the light emitted by various elements when heated to incandescence. They discovered that each element, when heated, emits light at specific characteristic wavelengths, a fingerprint of color unique to that element. Sodium emits a brilliant yellow-orange. Copper emits a blue-green. Each element has its own signature as distinctive as a voice. And crucially, they discovered that elements also absorb light at precisely those same wavelengths when cool gas is placed between a hot light source and an observer. The cool gas swallows its own characteristic colors from the passing light, leaving dark gaps, exactly the dark lines Fraunhofer had catalogued in the solar spectrum. This was the Rosetta Stone of astrophysics. The dark lines in sunlight were not defects or mysteries without answer. They were the absorption fingerprints of elements in the sun's outer atmosphere, cool gas absorbing its characteristic wavelengths from the light produced by the hotter layers below. Every dark line was a chemical signature. Every gap in the rainbow was a whisper from a specific element saying, "I am here. I exist in this star." Within years of Kirchhoff and Bunsen's discovery, astronomers applied spectroscopy to the sun and began identifying element after element in its atmosphere: hydrogen, calcium, iron, magnesium, sodium. The sun was not made of some exotic divine substance. It was made of the same elements found in Earth's laboratories, common, familiar periodic table elements, present in ratios that could be measured and quantified from 93 million miles away. And then came a line that nobody could match to any known element. In 1868, during a total solar eclipse, the French astronomer Jules Janssen and the English astronomer Norman Pogson independently observed a bright yellow line in the sun's chromosphere that did not correspond to any element then known on Earth. The English astronomer Joseph Norman Lockyer, studying the same observation, proposed that the line represented an element that existed in the sun but had not yet been discovered on Earth. He named it helium, after Helios, the Greek sun god. For more than 2 decades, helium was a purely solar element. It had never been detected on this planet. In 1895, the Scottish chemist William Ramsay found helium trapped in a uranium mineral on Earth, released by radioactive decay, slowly accumulating in pockets of rock over geological time. The element predicted by sunlight was real. It existed here too. The sun had told us something about Earth that Earth had not yet told us about itself. This moment helium discovered in the sun before it was found on Earth is one of the most elegant demonstrations in all of science of what spectroscopy makes possible. Light analyzed carefully carries complete chemical information about its source. Every star in the universe is broadcasting its composition continuously. We just needed to learn the language. Now, here is where the story of the sun's composition connects directly to its future. And the future of the sun is something that most people have never been told in a way that is both accurate and somehow peaceful. The sun will die. This is not a speculation. It is a certainty written in the same physics that explains why it shines. And understanding how it will die, the specific step-by-step sequence of changes it will undergo over the next 5 billion years, is one of the most complete stories in astrophysics. We know this story with remarkable confidence because we can observe other stars at every stage of the same process scattered across the galaxy, like pages from a book laid open at different chapters. Currently, the sun is in the middle of what astronomers call the main sequence, a phase of stable hydrogen fusion that accounts for the vast majority of a star's lifetime. The sun has been on the main sequence for about 4.5 billion years, and it has roughly 5 billion years left at its current state. During this phase, the balance between gravity pulling inward and the pressure of nuclear fusion pushing outward holds the sun in a near-perfect equilibrium, the hydrostatic equilibrium we discussed earlier. But that equilibrium is slowly, subtly shifting. As the sun fuses hydrogen into helium in its core, the core gradually accumulates helium, the ash of the nuclear reaction. Helium does not fuse under the sun's current core conditions. It is inert at these temperatures and pressures, so it accumulates. the helium core grows. And as it grows, the hydrogen-burning shell around it must move slightly outward to find fresh fuel. The shell burning intensifies. The sun's luminosity slowly increases. Researchers estimate the sun is currently about 30% more luminous than it was when it first formed, and it will continue to brighten gradually over its remaining main sequence lifetime. This slow brightening has significant implications for Earth. In roughly 1 billion years, less than a quarter of the sun's remaining main sequence life, the sun's increased output is expected to warm Earth enough to push it beyond what scientists call the habitable zone. The oceans would evaporate, water vapor would accumulate in the upper atmosphere, be split by ultraviolet radiation into hydrogen and oxygen, and the hydrogen would be lost to space. Earth would become more like Venus, hot, dry, dense with carbon dioxide. The oceans gone, the surface temperature eventually climbing to hundreds of degrees. Life as we know it would be gone, not suddenly, not catastrophically. Slowly over geological time, as the sun does what it has always done, shine a little more brightly each billion years, until Earth's delicate balance of temperature and water can no longer be maintained. This is not cause for the kind of existential despair that the word extinction might otherwise carry. 1 billion years is 40,000 times the entire span of human civilization. It is more than 3 times longer than the interval since the first complex animal life evolved on Earth. Whatever Earth contains in 1 billion years, if anything remains on it at all, will not be recognizable as anything we know today. The story will have moved on in ways as unimaginable to us as modern cities would be to the first bacteria. But the sun's story continues far beyond even that. About 5 billion years from now, after the hydrogen in the core is exhausted, something more dramatic begins. With no fusion in the core to produce outward pressure, gravity wins temporarily. The core contracts. It heats up. The temperature rises, and eventually it rises enough to ignite a new process, helium fusion. 3 helium nuclei can, under these conditions, fuse into 1 carbon nucleus. This is called the triple alpha process, because helium nuclei are also called alpha particles. And at a core temperature of about 100 million degrees, roughly 7 times hotter than the current sun, this new fusion begins. The energy output surges. The outer layers of the sun expand dramatically, not slightly, not gradually, but to an extraordinary degree. The sun's radius, currently about 700,000 kilometers, will swell to somewhere between 100 and 200 times its current size. It will become what astronomers call a red giant. A red giant sun will be large enough to engulf Mercury, possibly Venus. Whether it will engulf Earth depends on models that involve some uncertainty, particularly around how much mass the sun will have lost in stellar winds during its evolution, which affects how far Earth's orbit will have migrated outward. Some models suggest Earth narrowly escapes engulfment. Others suggest it is absorbed. Either way, it will have been uninhabitable long before this point. Have you ever looked at the night sky and noticed that some stars appear redder than others? Betelgeuse in the shoulder of Orion, that distinctly ruddy point of light, is a red supergiant, a much more massive star than the Sun in the late stages of its evolution. Aldebaran, the bright eye of Taurus, is a red giant. When you look at those stars, you are looking at something real and present stars that have exhausted their core hydrogen and expanded outward exactly as the Sun will do in 5 billion years. The Sun's red giant phase will last roughly 1 to 2 billion years. During this time, the helium in the core will itself be exhausted, replaced by carbon and oxygen, the ash of helium fusion. And now, the Sun faces a decision point determined entirely by its mass. Mass is the master variable of stellar evolution. It determines almost everything about how a star lives and how it dies. Stars much more massive than the Sun, 8 times the Sun's mass or more, have enough gravity to compress their cores to temperatures sufficient to fuse carbon, then neon, then oxygen, then silicon. each stage producing a new element as the ash of the previous reaction becomes the fuel of the next. This process continues until the core is iron, the endpoint of nuclear fusion, the element from which no further energy can be extracted. And then catastrophically, the core collapses in milliseconds and the star tears itself apart in a supernova, an explosion so bright that a single dying star can outshine an entire galaxy of hundreds of billions of other stars. The sun will not do this. The sun is not massive enough. When the sun's helium is exhausted, its core now carbon and oxygen will not be compressed enough to ignite carbon fusion. Gravity will squeeze it, but not to the temperatures required. Instead, the outer layers of the sun, no longer supported by fusion pressure, will drift away into space over tens of thousands of years, expanding outward as a slowly glowing cloud of gas called a planetary nebula. The name is misleading. Planetary nebulae have nothing to do with planets. Early astronomers, through small telescopes, thought they resembled the round disks of planets, and the name stuck. Planetary nebulae are among the most beautiful structures in the universe. The Helix Nebula, about 650 light-years away, is sometimes called the Eye of God, a ring of glowing gas surrounding a tiny, intensely hot central star, expanding slowly into the surrounding space. The Ring Nebula in Lyra, the Cat's Eye Nebula, the Butterfly Nebula. Each one is the shed skin of a dead star, the remnant of outer layers dispersed into space while the core remains behind. And what remains behind is what the sun will become, a white dwarf. A white dwarf is approximately the size of Earth, roughly 12,000 kilometers in diameter, but containing the mass of the sun compressed into the small volume. The density is extraordinary. A teaspoon of white dwarf material would weigh approximately 5 tons. It is not fusing. It is not burning. It is simply hot, enormously hot, at first radiating the thermal energy stored in its compressed matter. And it is slowly cooling. Slowly. The time required for a white dwarf to cool to darkness is longer than the current age of the universe. The universe is approximately 13.8 billion years old. A white dwarf cools on timescales longer than that. So long that in the current universe, no white dwarf has yet had time to cool completely to a black dwarf, a cold, dark, invisible remnant of a once-living star. Black dwarfs are theoretical objects. None yet exist because the universe has not been around long enough. The sun's white dwarf will radiate its stored heat for billions and billions of years. It will fade from white to yellow, to orange to red, to deep infrared to invisibility, on time scales that dwarf the sun's entire fusion lifetime. And eventually, in the unimaginably far future, it will be cold and dark and still. A dead star. A remnant, an ember. Here is what makes this story for me feel not like an ending, but like a completion. The carbon in your body, the carbon that forms the backbone of every biological molecule in your cells, that constitutes a significant fraction of your mass, was not made in the sun. The sun has not yet fused hydrogen all the way to carbon in significant quantities. The carbon in you was made in stars that lived and died before our solar system formed. In the cores of ancient red giants through the triple alpha process billions of years before Earth existed. When those stars shed their outer layers in planetary nebulae, or tore themselves apart in supernovae, they scattered their carbon, oxygen, nitrogen, iron, and dozens of other elements into the interstellar medium. And that material eventually collapsed under gravity, along with hydrogen and helium from the Big Bang to form the sun and the planets, including Earth and everything on it. You are made of the ash of ancient stars. Your carbon, your oxygen, your iron, they were forged in nuclear furnaces that burned out before the sun was born. The sun, in burning its hydrogen into helium, is continuing a process of nuclear cooking that the universe has been doing since its first few minutes. Building heavier elements from lighter ones, transforming mass into light. And eventually, when our sun disperses its outer layers in a planetary nebula, 5 billion years from now, Those layers enriched with the helium and some carbon that the sun will have produced will drift outward and become part of the raw material for future stars, future planets, and perhaps future life. Nothing is wasted, nothing ends completely. Matter transforms, energy transforms. Stars live and die, and their remnants become new stars. The universe is not diminishing, it is cooking. Slowly, patiently over time scales that make human history invisible, it is building complexity out of simplicity, structure out of chaos, life out of hydrogen. Does it change how you see the sun, knowing it is mortal? Knowing that the steady, reliable fire that has been there every morning of every human life that has ever been lived, that it has a future and an ending, as all things do. I think there is something quietly beautiful in that. The sun shines not because it is eternal. It shines because it is using what it has as efficiently as it can for as long as it can. And in doing so, it has given this one small planet enough warmth and light to produce forests, oceans, weather, thought, music, and the capacity to look upward and ask what it is. The sun is dying. And it is dying in the most generous, most profligate, most magnificent way. Imaginable 4 million tons of itself, converted to light every second, given freely to everything within reach for 10 billion years. That is not a tragedy, that is a kind of grace. And yet, the story of the sun is not only the story of one star, because the sun, middle-aged, unremarkable, perfectly ordinary by galactic standards, turns out to be one of the most scientifically valuable objects in the universe, precisely because of how ordinary it is. It is the star we can study up close, the one whose details we can measure directly. And what we have learned from it illuminates everything else out there, every point of light in a clear night sky, every galaxy in the deep field, images from our greatest telescopes. What the sun tells us about the universe, and what the universe tells us about itself through the sun, is a story that goes far beyond one star's lifetime. That is the story that opens up right now. The sun is ordinary, genuinely, thoroughly, unremarkably ordinary. Among the estimated 200 to 400 billion stars in the Milky Way galaxy, the sun sits squarely in the middle of every significant category: mass, temperature, luminosity, age, chemical composition. It is not the largest star in the galaxy. It is not the smallest. It is not the hottest or the coolest. It is not particularly young or unusually old. It is by every measure astronomers use to characterize stars a textbook example of mediocrity. And that mediocrity is perhaps the most scientifically valuable thing about it, because the sun is close. It is 149 million kilometers away, a distance that sounds vast, but is nothing compared to the next nearest star, Proxima Centauri, at about 40 trillion kilometers. The sun is so close that we can measure it, study it, probe it with spacecraft, read its magnetic field, watch its surface convect in real time, and detect the individual particles it streams outward. No other star comes remotely close to offering us that kind of access. And because it is ordinary, everything we learn about the sun applies with appropriate scaling for mass and composition to the vast majority of stars in the universe. The sun is not just a star we happen to live near. It is the Rosetta Stone of stellar astrophysics, the one star from which all others can be understood. Let us begin with the Hertzsprung-Russell diagram, because it is one of the most important visualizations in the history of science, and almost no one outside of astronomy has ever heard of it. In the early 20th century, two astronomers working independently, Einar Hertzsprung in Denmark and Henry Norris Russell in the United States, began plotting stars on a graph. The horizontal axis represented temperature-hot stars on the left, cool stars on the right. The vertical axis represented luminosity, intrinsically bright stars on top, dim ones on the bottom. And when they plotted large numbers of stars on this diagram, a structure emerged that no one had predicted. The stars did not scatter randomly across the diagram. They clustered. The vast majority, including the sun, fell along a diagonal band, stretching from the upper left to the lower right, from hot and bright to cool and dim. This band is called the the main sequence. Below and to the left of the main sequence sat a cluster of small, hot, dim stars, white dwarfs. Above and to the right sat enormous, cool, luminous stars, red giants. And scattered in the upper left were the rare, brilliant blue supergiants and white-hot stars of exceptional mass and energy. What Hertzsprung and Russell had unknowingly created was a map of stellar evolution. The main sequence is not just a grouping of similar stars. It is where stars spend most of their lives fusing hydrogen into helium. The red giant branch shows stars that have exhausted their core hydrogen and begun to expand. The white dwarf region shows the remnants of stars that have completed their evolution, the entire life history of a star written in a two-dimensional graph of temperature versus brightness. The sun sits comfortably in the middle of the main sequence. Knowing where the sun sits and understanding what the main sequence means physically allows astronomers to determine the age, mass, evolutionary stage, and future of every other star that can be plotted on the same diagram. The sun provided the reference point. The rest of the universe was mapped from there. There is a number that connects the sun to the entire observable universe in a way that is, when you first encounter it, almost too large to process. That number is the estimated count of stars in the observable universe, approximately 10 to the power of 24. 1 septillion, a 1 followed by 24 zeros. Of those, approximately 90% are smaller and cooler than the sun-red dwarfs, the most common stellar type burning hydrogen so slowly that they could shine for trillions of years, far longer than the current age of the universe. About 9% are roughly similar to the Sun, G and K type main sequence stars, and about 1% are more massive than the Sun, shining more brilliantly, but burning through their fuel far more quickly, some lasting only millions of years before dying in supernovae. Every one of those septillion stars is fusing hydrogen. Every one of them is converting mass into energy through the same proton-proton chain, or in more massive stars, through a related cycle called the CNO, cycle carbon-nitrogen-oxygen, in which those elements serve as catalysts for fusing hydrogen into helium, operating at the higher core temperatures that larger stellar masses produce. Every one of them is slowly building up helium ash in their cores. Every one of them is following a path through stellar evolution that the Hertzsprung-Russell diagram maps with extraordinary accuracy. All of that, the entire framework for understanding the universe's stellar population, was built on measurements of the one star close enough to study directly. Now let us talk about something called stellar nucleosynthesis, because it connects the sun not just to other stars, but directly to you, to the atoms in your body, the iron in your blood, the calcium in your bones. The idea was developed in a landmark 1957 paper by William Fowler and Fred Hoyle, along with Jeffrey and Margaret Burbidge. The paper, known simply as B2FH, from the initials of its four authors, laid out for the first time a comprehensive theory of how every element heavier than hydrogen and helium was produced in the interiors of stars or in the violent explosions of dying ones. Hydrogen and helium, the two lightest elements, were produced in the first few minutes after the Big Bang in a process called Big Bang nucleosynthesis. Everything heavier, lithium, beryllium, carbon, nitrogen, oxygen, silicon, iron, gold, uranium, was made later inside stars or in the extreme conditions of stellar explosions. The sun is currently producing helium from hydrogen. When it eventually becomes a red giant and begins the triple alpha process fusing helium into carbon, it will contribute carbon and some oxygen to the interstellar medium through its eventual planetary nebula. More massive stars take this further. Carbon fuses into neon and magnesium. Neon fuses into oxygen and silicon. Silicon fuses into iron. Each stage requires higher temperatures and produces heavier elements like a factory running progressively hotter furnaces to process increasingly stubborn raw materials. But iron is the end of the road. Fusing iron does not release energy. It requires energy. When a massive star's core becomes iron fusion stops, pressure drops, and the core collapses catastrophically. The resulting supernova explosion creates conditions of extreme density and temperature in which elements heavier than iron can be produced: gold, platinum, silver, uranium, in a process called neutron capture, where atomic nuclei rapidly absorb neutrons and build upward to heavier and heavier elements in fractions of a second. The gold in any piece of jewelry you own was made in a supernova, or possibly in the collision of two neutron stars, events so energetically extreme that they briefly outshine entire galaxies. The heavy elements in your body were forged in stellar violence billions of years before the Earth existed. This brings us to one of the most frequently misquoted, most poorly understood, and most genuinely profound statements in popular science: the claim that we are made of stardust. It is true, but the full picture is more specific, more layered, and more beautiful than the phrase usually conveys. The hydrogen in your body, in the water that makes up roughly 60% of your mass, in the organic molecules that constitute your cells, that hydrogen is not stardust. It is primordial. It came directly from the Big Bang 13.8 billion years ago, never having been inside a star. The hydrogen in you is almost as old as the universe itself. The carbon in your body, in every carbon-based molecule in your cells, the backbone of all organic chemistry, was made in the triple alpha process in the core of a red giant star that died before our solar system formed. It was dispersed into the interstellar medium in that star's planetary nebula, mixed into the gas cloud that eventually collapsed to form the Sun and Earth, and incorporated into the rocky material from which Earth was assembled. The oxygen you breathe, largely produced in the cores of massive stars and dispersed in supernovae. The iron in your hemoglobin, forged in the late-stage fusion of a massive star, or formed in a supernova's iron group nucleosynthesis. The calcium in your bones, produced in silicon burning in massive stellar cores. The iodine in your thyroid, the copper in your enzymes, the zinc in your immune system, all of them trace back to specific nuclear processes in specific stellar environments at specific moments in cosmic history. You are not metaphorically made of stars. You are literally assembled from the nuclear outputs of stars that lived and died across billions of years of cosmic history. The sun sits in the middle of that story, currently fusing hydrogen, eventually contributing carbon and oxygen, one chapter in a book that began at the Big Bang and has no visible ending. Have you ever stood outside on a clear night, far from city lights, and looked at the Milky Way? That soft, pale band stretching across the sky? Not quite a cloud, not quite a solid thing. Almost like breath on cold glass is the combined light of hundreds of billions of stars, most of them too faint to see individually, all of them blending into that soft, luminous river. Each point of light in that band is a nuclear furnace, each one converting mass into energy, each one aging according to its mass and composition. Some of them are surrounded by planets. Some of those planets may have oceans. Some of those oceans may have something living in them, looking upward at their own night sky, wondering the same kinds of things. The sun is one of those points of light. From a sufficient distance, say from the Andromeda Galaxy, 2.5 million light-years away, the sun would not be individually visible. It would be lost in the glow of the Milky Way, indistinguishable from 200 billion other stars. Ordinary, anonymous, unremarkable, and from that tiny, ordinary, anonymous star, everything. The oceans of Earth, the evolution of life across 4 billion years, civilizations, languages, mathematics, music, the capacity to look outward and ask what the universe is made of. All of it powered by 4 million tons of solar mass, converted to light every second, from an unremarkable G-type star in the outer arm of a thoroughly typical spiral galaxy. The universe makes life the way it makes everything else, patiently, abundantly, without preference. It shines equally on everything within reach. It asks nothing back. There is a common misconception worth addressing here, because it comes up whenever people think about the sun's relationship to life on Earth. The assumption is that the sun was made for Earth, that its size, its temperature, its position were somehow configured to produce a habitable planet with water and moderate temperatures, and the right mix of radiation for photosynthesis to evolve. The reality is the reverse. Life on Earth evolved to fit the sun it got. Photosynthesis works with the specific wavelengths of light that the sun's photosphere produces, because life evolved on a planet bathed in that light for 4 billion years, and natural selection favored organisms that could harvest it efficiently. If Earth orbited a different type of star, a cooler red dwarf, a hotter blue star, the organisms that evolved there, if any did, would use different wavelengths, different chemistry, different mechanisms. The sun did not adapt to life. Life adapted to the sun. The sun arrived first, and it has been shining with the same steady spectrum for 4.5 billion years. And the entire biosphere is, in a very real sense, a complex machine built to harvest its output. This is not a diminishment of life's wonder. It is an expansion of it. Life does not require a special sun. It requires a star of some kind and time and chemistry. The universe supplies all three in enormous quantities. The question of whether life exists elsewhere around other ordinary stars, in other ordinary solar systems, in other ordinary galaxies, is not whether it is possible. It is whether we will someday have the means to find it. The study of the sun has given us more than astrophysics. It has given us a framework for thinking about where we are in the universe, not at the center, not specially placed, not the destination that everything was arranged toward, but as one expression of a process that is happening in various forms everywhere. Every star is a version of the sun, larger or smaller, hotter or cooler, older or younger, but running on the same physics ending by the same rules, contributing its nuclear outputs to the same ongoing cosmic chemistry. And every planet around every star is in some way a version of the experiment that produced us matter, organized by physics and chemistry and time testing what it can become. The sun is ordinary, and the universe, it turns out, is full of ordinary things that, when given enough time and the right conditions, become extraordinary. There is one last piece of the sun's story that we have not yet told, the most intimate piece, the one that closes the distance between a star and a human being more completely than any fact about mass or luminosity or fusion can. It is the story of what the sun means in the context of ending of last light and silence, and what remains when something that has been present for a very long time is finally gone, and it circles back gently to where we began tonight, a quiet sky, a fire that has always been there, and a question about why. That is where our final part of tonight's journey leads. We began tonight with a simple question. How does something burn for 4.5 billion years without going out? And over the course of this journey, from ancient temples aligned to the solstice, to Lord Kelvin's confident wrongness, to the nuclear furnace at the center of a star, to a photon's 100,000-year odyssey, through dense plasma, to the inevitable graceful death of a star that will one day shed its outer layers like a silk robe into the dark, we have arrived somewhere unexpected. Not just at an answer, at something larger than an answer. Because the question was never really only about the sun. It was about us, about what we are made of, where we came from, how long we have been here, and what it means to exist on a small, warm planet circling an ordinary star in the outer arm of a spiral galaxy that contains 200 billion other stars, which is itself one of roughly 2 trillion galaxies in the observable universe. That is where we are. That is the address. Let us spend a few minutes with something that almost never gets discussed when people talk about the sun, and that is the question of human timescale versus solar timescale, and what the contrast between them reveals about the nature of meaning. The sun has been shining for 4.5 billion years. Modern Homo sapiens, our species anatomically and behaviorally modern, has existed for roughly 300,000 years. That is 0.0067% of the sun's current age. If you compress the sun's entire lifespan so far into a single calendar year, January 1st to December the 31st, Modern humans would appear at approximately 11:59:38 p.m. on December the 31st, 22 seconds before midnight. All of recorded human history, every civilization, every war, every discovery, every piece of art or music or literature ever created fits into roughly the last 1 second of that compressed year. Less than 1 second. The pyramids of Giza, built about zero point 0.3 seconds ago in solar time. The Roman Empire, about 0.14 seconds ago. The entire Industrial Revolution, which transformed human civilization more profoundly than perhaps any other single development, about 0.007 seconds ago. A blink so small it barely registers. And yet, in that 1 second, that vanishingly thin sliver of solar time, we built everything. Languages, mathematics, medicine, telescopes that can see light from 13 billion years ago, spacecraft that have left the solar system entirely, a set of equations called quantum mechanics that describes with precision that has never been exceeded in the history of science the behavior of matter at scales so small they cannot be seen with any instrument we have built. In 22 seconds of solar time, we figured out how the sun works. There is something in that contrast that I find simultaneously humbling and exhilarating. We are so new. The sun was already old before the first fish developed a backbone. It was already middle-aged by the time the first dinosaur evolved. It has seen more than you can imagine in the way that a mountain sees things not consciously not caring, but present throughout, unchanged in its essential nature through all of it. And we arrived very recently, and we looked up and we asked why. Not every species looks up and asks why. Most life does not. The sun has shone on 3.7 billion years of biological evolution on this planet. And for almost all of that time, nothing looked at it and wondered. Single-celled organisms, early multicellular life, fish, amphibians, reptiles. The vast majority of mammalian species, none of them turn their face toward the sun and reach for an explanation. We did. We do. It is perhaps the most distinctly human thing about us, not that we are the only species that uses tools or communicates or lives in social groups, but that we look at the thing that warms our faces and feel compelled to understand what it is. The understanding we have now, nuclear fusion, the proton-proton chain, hydrostatic equilibrium, stellar evolution, spectroscopy, neutrino, oscillation, did not arrive complete and polished. It arrived in fragments across generations, assembled by hundreds of people who each contributed a piece without seeing the final picture. Marie Curie in her leaking shed, Ernest Rutherford firing alpha particles at gold foil, Cecilia Payne-Gaposchkin, whose 1925 doctoral thesis was the first to correctly identify hydrogen as the dominant element in stars, a conclusion so unexpected that her male supervisor, Henry Norris Russell, convinced her to qualify it as spurious in her published work. 4 years later, Russell reached the same conclusion, independently published it, and received much of the credit. Payne-Gaposchkin, whose work was later called undoubtedly the most brilliant PhD thesis ever written in astronomy by the astronomer Otto Struve, spent decades working in the shadow of colleagues who had initially dismissed her most important finding. Her name deserves to be remembered tonight, because the knowledge that the sun is mostly hydrogen, the foundational fact from which almost everything else about solar physics follows, was first correctly understood by a 25-year-old woman who was told she was probably wrong. She was not wrong. She was simply early. This is how science actually works. It is not a clean, triumphal march from ignorance to knowledge. It is messy human, often unfair, shaped by the accidents of who happens to be in what laboratory at what moment, and whose work happens to receive recognition. The sun does not care about any of this. It keeps burning regardless. But the story of how we came to understand it is inseparable from the story of human beings, with all their brilliance and all their limitations, trying to see something true. There is a spacecraft called Voyager 1 that was launched in September 1977. It has been traveling outward from the Sun at approximately 17 kilometers per second, ever since fast enough to cross the continental United States in about 4 minutes, fast enough that in the 47 years since its launch, it has traveled more than 23 billion kilometers from Earth. In 2012, Voyager 1 crossed the heliopause, the boundary where the solar wind streaming outward from the Sun becomes too diffuse to push back against the interstellar medium. It became the first human-made object to enter interstellar space. It is still transmitting. Faintly, its signal by the time it reaches Earth has a power of about 20 femtowatts, 20 million times weaker than the signal from a typical cell phone. But it transmits and we receive it and we know where it is. 23 billion kilometers away, crossing through the cold, nearly empty space between the stars, carrying a golden record with sounds and images of Earth. Whale songs, a Bach fugue, greetings in 55 languages. A diagram showing the Sun's position relative to 14 pulsars so that any finder might locate us. Voyager 1 is powered by the decay of plutonium-238 nuclear energy, the same fundamental physics that powers the Sun, compressed into a small thermoelectric generator the size of a kitchen appliance. It will continue transmitting until roughly 2025 before its power becomes insufficient. Then it will fall silent, and it will continue traveling outward into the dark for millions of years, long after every structure humans have ever built on Earth has crumbled to dust. In about 40,000 years, it will make its closest approach to a star, a red dwarf called Gliese 445, passing within about 1.7 light-years of it. It will not stop. It will continue outward, a small silent emissary from a species that existed briefly on a planet warmed by an ordinary star that looked up, that wondered, that built something capable of crossing into the space between the stars. Do you ever think about what it means in the largest sense to be alive right now? Not in a historical sense or a political sense, but in a cosmic sense. To be a collection of atoms that were forged in stellar interiors across billions of years, assembled by chemistry and evolution, into something that can sit quietly in the dark and think about where those atoms came from. The iron in your blood carries oxygen to your brain, and your brain generates the electrical patterns that constitute thought. That iron was made in the core of a dying star. The oxygen was made in a supernova. The carbon backbone of the molecules doing your thinking was made in the triple alpha process of a red giant's final years. The hydrogen in the water that makes up 60% of your body came from the Big Bang itself. You are not just connected to the stars, you are assembled from them. And you have uniquely among all the arrangements of matter on this planet the capacity to know that, to hold it in your mind, to feel the weight of it on a quiet evening, looking up at a sky full of nuclear furnaces and understand even partially what you are looking at. That capacity, the capacity to understand, is not nothing. In a universe mostly filled with hydrogen gas and empty space and the cold silence between galaxies, it is, as far as we know, extraordinarily rare. And it is powered right now by the sun, by the warmth that grew the grain that fed you, by the light that feeds the green things that feed the animals that built the civilization in which you learned to read, by 4 million tons of solar mass converted to energy every second, given freely without condition to everything within reach. Carl Sagan, the astronomer and writer, who perhaps more than anyone else communicated the emotional weight of cosmological knowledge to a general audience, wrote in his 1980 series, Cosmos, that we are a way for the universe to know itself. Not a poetic metaphor, but a description of something physically real. The universe produced matter. Matter organized itself under gravity and chemistry into stars. Stars built heavier elements. Those elements assembled into planets. On at least one planet, chemistry produced life. Life produced nervous systems. Nervous systems produced minds. And our minds look outward and recognize with growing clarity the processes by which all of this came to be. The universe through us is doing something it could not do through hydrogen gas or empty space, or even through most of the life that has ever existed on Earth. It is reflecting on itself, asking what it is, measuring its own age, tracing its own history, reading the absorption lines in its own starlight. And the sun makes this possible, not just in the trivial sense that it provides energy for life, but in the deeper sense that it is the star close enough, ordinary enough, and patient enough to let us study it until we understood it. And in understanding it, we began to understand everything else. We began tonight with a question about fire. How does something burn for 4.5 billion years? The answer we now know is this: it does not burn. Not in the way a candle burns, consuming itself in a chemical reaction that produces light and heat from oxidation. The sun does something far stranger, far older, far more fundamental than burning. It converts matter into energy directly at a rate of 4 million tons per second through the fusion of hydrogen nuclei in a core where the temperature and pressure push quantum mechanics to its limits. It has been doing this since before Earth existed. It will continue doing this for another 5 billion years. And when it finally exhausts its hydrogen, it will expand into a red giant shed, its outer layers in a glowing planetary nebula, and leave behind a cooling white dwarf that will quietly fade over time scales longer than the current age of the universe. And the atoms it disperses into the interstellar medium, the carbon and oxygen and helium it has spent 10 billion years producing, will drift outward into the galaxy, and eventually under gravity, they will be drawn into new gas clouds, and those clouds will collapse, and new stars will form, and some of them will have planets, and some of those planets will be warm, and some of those warm planets may have chemistry that becomes biology, and some of that biology may produce something with a nervous system complex enough to look upward on a quiet night and ask the same question we asked tonight. How does something burn for billions of years? And the answer will come slowly from the same direction, from the light. There is a kind of peace in knowing this and understanding that the sun's story is not a story about exception or miracle or divine design, but about the ordinary operation of physics applied at astronomical scales across geological time. The universe is not performing for us. It is not structured around us, and yet it produced us, not by intention, but by the patient application of the same rules to an unimaginable variety of conditions over an unimaginable span of time. We are not the point of the universe. We are one of its outcomes. And that, I think, is more wonderful than being the point. The sun will be there in the morning, same as it always has been, same as it has been for every morning of every human life ever lived, burning its 4 million tons per second, warming this small blue planet in its small, quiet corner of a spiral galaxy that is itself one of 2 trillion, ordinary, steady, ancient, generous. And now, tonight, you know what it is. You know what it is actually doing deep in its 15 million degree core in the 10 seconds it took you to breathe just now, in the quiet time between where you are and where sleep is waiting. You know the story of the photon that traveled 100,000 years inside a star to reach your face this morning. You know the names Kelvin, Curie, Bethe, Payne, Gaposchkin, of the people who built the understanding piece by piece, often in the dark, often without recognition, because the question was too beautiful not to answer. And you know that the light from the sun is not just light. It is transformed mass. It is nuclear history. It is the same process that built the carbon in your cells and the oxygen in your lungs and the iron in your blood. It is old before your species is young. It will continue long after every story any human has ever told has been forgotten. And it will still, on some future morning, we cannot imagine be rising somewhere. Thank you genuinely, quietly, warmly for spending this night with the sun, for letting curiosity do the listening, for sitting with these ideas long enough to feel their weight, not just their surface. Science told softly is still science. The proton-proton chain is just as real, whether it is spoken in a lecture hall or whispered in the dark. And I think there is something true about the idea that the best way to receive knowledge, this large knowledge about stars and atoms and the age of the universe and the origin of the atoms in your body, is slowly, gently, with room for it to settle. If this journey felt like something worth taking, if you find yourself thinking about the sun differently the next time it rises, please leave a like. It is a small gesture, but it tells the next curious person that this is a place worth finding. And if you want to know when the next quiet story is ready, subscribe and ring the bell, not for noise. For the next night, when you want to understand something large before you sleep. The next story is waiting. It is about something that moves more slowly than the photon we followed tonight and has been traveling far longer and carries within it a kind of beauty that I think you will want to sit with. Rest well. The sun is still burning. The universe is still assembling itself atom by atom from the inside out. And somewhere in the heart of a star, right now, a photon is being born that will spend 100,000 years looking for the way out. Sleep gently. Good night.